Hello, thank you for joining us today at the Charge Virtual Conference on EV engineering. And the topic of this session is what testing equipment do we need now for tomorrow's EV batteries? And it's brought to you by EA Elektro-Automatik. There will be a Q&A session after the presentation, so please do submit your questions at any point by clicking the Q&A button on your screen. And a recorded video of the presentation will also be available to view on demand after the session is completed. You can visit the session's registration page on our site for more details. Our speakers today are Russ Gaubatz, battery subject matter expert, and Connor Peck, applications engineer, both from EA Elektro-Automatik. Welcome.
Hello, my name is Russ Gaubatz. I'm the Senior Applications Engineer here at EA Elektro-Automatik. Thank you for joining. I will be presenting EV battery test equipment and the rapid expansion of the EV battery industry. The purpose of this webinar is to discuss the enhancement of EV battery production for companies who are testing batteries. This will go over the growing market demand for higher power batteries and what should be taken into consideration with this expanding market. We will be covering demand of EV test equipment, higher power, space for production, higher test voltages, throughput bottlenecks, safety concerns, training, costs and energy usage, and the types of test systems available. EV vehicles and their rapid growth starts with utilizing lithium-ion battery technology, with new types of batteries coming out all of the time. These new batteries are much lighter in weight, have less risk of overheating due to environmental temperatures, and are much more energy efficient. In North America and Europe, the most common material for battery manufacturing includes, but is not limited to, cobalt, nickel, and manganese. In China, lithium iron phosphate is more commonly used for battery production. Each battery operates different from one another, with some batteries having a slow charge-discharge and some with a faster charge-discharge. Battery tests will vary depending on the circumstances of the test, the user in control of the test, and to what extent they would be using the battery for. The new batteries include new manufacturing material for the expansion of better batteries. With the invention of the lithium-ion battery, it has enabled manufacturers to expand the possibilities for independent source applications. Lithium-ion also has negative side effects of thermal runaway. This is caused by heat vaporizing the electrolyte, which pressurizes the cell casing. When the case fails, flammable gases are released, spreading into the atmosphere. This can cause the battery to heat up and catch fire, which is very hard to extinguish due to the self-supply of oxygen. Additionally, when the case fails, it can also send shrapnel through the surrounding cells. As an example, when an EV fire occurred while driving down the highway, the driver was forced to pull over and escape quickly off the side of the highway. When firefighters arrived on scene, they discovered the battery pack of the EV had caught fire. With temperatures reaching up to 1,000 degrees, with toxic fumes emitting from the car, firefighters struggled putting the flames out with 30,000 gallons of water to cool the unit down. They even had to request assistance from the next town's fire department. Understanding the science behind thermal runaway is as follows. If a battery is overcharged or charged at a high current, it can cause metallic lithium to form within the battery. It is highly reactive and can cause a fire if it encounters other materials within the battery. The plated out lithium can eventually form short circuits between internal battery components. Many of these factors are caused by the misuse and neglect of the battery. It is important to follow a procedure when handling batteries, especially if they are lithium-ion. Testing also has safety concerns. A manufacturer in the Midwest built an event-proof bunker inside the plant. This was to house the battery test area. As each test varies, some tests may not require as much protection. Each test has environmental parameters such as surrounding temperature, humidity, salt, altitude, water, dust, and chemical. It is important to ask, is this battery at any risk during the testing? If so, what can be done to prevent or lower the risk? Battery recyclers sometimes choose to grind down batteries while in a water bath for safety reasons. This causes their black mass to be wet and not worth as much when purchased. or they have to dry it out with dryers, causing even more cost and energy waste. Another solution is to discharge these batteries before shredding with a regenerative load. This allows them to not only benefit from the energy recovery, but also gets more money for their black mass. New battery types, such as zinc air and graphene, are in development for industry. This may cause tests to vary, but the system is not exclusively linked to one test due to the three common factors of batteries: voltage, current, and power. Advantages to using a solid-state battery. It has a high energy density. It can store more charge in a compact size compared to traditional batteries, giving you longer driving range and peace of mind. But that's just scratching the surface. Solid-state batteries also boast an impressively long lifespan, quick charging capabilities, and low maintenance requirements. This is important to note, as the industry is increasing, and so is the demand for creating batteries with higher charge capacity. This can allow for the use of independent source applications, like electric cars, to have the longer battery life for traveling distances greater than 300 miles on one full charge. It is predicted that the first round of cars capable to having this ability will be achieved in the next couple of years. In comparison to a lithium-ion battery is the equivalent material of lithium sulfur. This material allows for a much longer lifespan of charge than the standard lithium-ion battery, as well as being more affordable to produce in mass quantities to meet the great demand of high energy density, enhanced safety, and cost effectiveness. Lithium-sulfur batteries are regarded as one of the most promising candidates for the next generation rechargeable batteries. The idea of having battery-powered cars and not having a combustion engine application is to make the environment cleaner. The idea of eliminating the mass production of greenhouse gases through the start of electric cars makes this material even more valuable. Lithium-sulfur produces less of a carbon footprint since it does not include cobalt. The major downside to the production of these batteries, and why the application has not been heard a lot in the industry, is its short lifespan. The life expectancy is much shorter than the lithium-ion battery. Therefore, it is not yet feasible to place these in electric cars. Lithium-ion and lithium-sulfur are not the only types of battery material being used in the industry. Graphene is also another lead for EV technology and has advantages over the use of lithium-ion. The material is much lighter, which can allow for electric cars to traverse longer range. This material is much stronger, having the ability to dissipate heat more efficiently. This puts a massive advantage over lithium-ion as it allows for tests to run safer for more tough environments and less likely of having an event. The material is also able to recharge faster and hold more energy, which can eliminate those long wait times for charging an electric car. Manufacturing batteries from this material is costly and hard to scale, which limits the adoption of these batteries. Nevertheless, changes in the industry will impact test equipment. The key factor is the battery power specifications: voltage, current, and power. All batteries have this, but at different levels. This is a factor in the industry that will remain a constant. The battery test system doesn't care what material the battery is based on, whether it be lithium-ion or potatoes. The test will vary, which will determine which type of equipment needs to be used based on the power specifications. Several changes, like the use of a new material, will affect the battery industry's production, changes in power specifications, lifetime, and durability. There are a lot of batteries, and how will they affect my test system? We will be talking about the throughput, power, safety, and where that will all be placed on the production floor. This webinar is aimed to explain what technologies are available to adapt to these massive changes in industry, with the goal to understand how to plan with this growing market on the rise. Growth of the EV battery world has forecasted several new and exciting opportunities. Such opportunities include the goal that by the year 2030, 30% of combustion engine cars become fully electric. The growth of the market has demanded the growth of the infrastructure, with new battery production plants opening nationwide, which is now pushing several companies to get into this market as quick as possible. This is demanding more production sites to be constructed, with 45 new battery plants opening in the US. Ensure that your battery testing is on pace to grab as much of the market as possible. One thing we notice is that customers have wanted to produce more battery tests, but do not have a full solution to do so. This has put a gap in the market for turnkey battery testing solutions. Furthermore, the rapid growth has pushed for the expansion of stronger batteries with much larger capacity. This requires stronger test equipment and more room on the production floor to meet the demands. To put this into perspective, a battery manufacturer was growing. Their battery test system was limited to 2 megawatts. Although they were building a new plant, most of the space was reserved for production, leaving little room to add test equipment. Their new test system is expandable to nearly twice the power in a third of the space that the old system would need. A key consideration was power density. Because there was limited room to add more test racks, the system they chose needed 1/3 of the space of their existing system for the same amount of power. An example of this growth is shown as these 4 racks that hold 1.5 megawatts of power in 4 cabinets. This illustrates a small footprint of the EA24U and 42U cabinets. This is controlled by one computer known as the PCMC, listed on the right, which ties the 4 racks into a BTS system for a smaller configuration of high power density. We can place our units into a 24U cabinet, which could hold up to 120 kilowatts, including the BTS, or 180 kilowatts of power without. The automotive industry is seeing a massive jump in battery storage capacity, with a 400-volt increase from prior battery technology for cars. Batteries for trucks, trains, and even planes are in development that will require testing at even higher voltages. The jump causes the demand for higher voltage testing to increase, putting industries at a higher nominal voltage rating than the average battery test system. These tests can range from the airplanes to trucks, running on these higher voltage batteries with much longer charge. With higher voltage comes the demand of selecting different test systems, with some test systems having the capability of running through 1,000 volts. Manufacturers need to test systems with headroom for their maximum voltage so that they can test at a higher voltage as batteries evolve. As of the past week, these electric and hydrogen power vehicles are being released into production as this new battery demand is expanding. Weight is the main reason for increasing voltage. This is due to smaller wires and a decrease in heat due to increased voltage and range efficiency if the car is lighter. This is why we want to test voltage at a higher rating. Demand is growing, which means your throughput must be able to grow. If a line goes down, then you lose throughput. With a modular solution, if one power supply in the rack fails, then operators can shut off that unit and continue to test at less than maximum power. Just replace the faulty power supply, and in 15 minutes, you're back online with full power. Ask your supplier, as part of an SLA, to keep the spare power supplies at the supplier or keep spare units on location. Take, for example, a battery maker was using a battery test system that was not modular. When one power supply in the rack failed, the entire test line went down, while managers waited weeks for the supplier to send a technician. After the technician arrived, he had to order parts and later return to finish the repair. This was a throughput nightmare. Installation and repair can be effected with easy access to the modular unit, and if the technician is properly trained to work on the device. An example of this is an EA Industrial Series power supply, which offers easy access for modular installation, with each unit having its own custom space in the cabinet, as well as easy-to-find information displayed on either the front or rear of the device. Let's say you have a 300 kilowatt BTS from EA. You happen to have one of the 60 kilowatt modules fault out. No problem. Shut off the faulty device and continue running with a maximum power of 240 kilowatts. If you happen to have a spare on site, turn off the device, remove and replace the 60 kilowatt unit, turn it back on, check the configuration, and continue at full power within 15 minutes. Another issue with throughput is the software that runs the test. Test requirements change with product changes and as the industry evolves. A change may need to be made quickly, which can be difficult with custom software. Even if the software runs on a standard program, there are issues with third-party software such as managing updates and additional costs. Some battery test system suppliers include software with their systems, avoiding these issues. These are designed for EV battery testing and can include test scripts. However, they may have limitations that custom software doesn't have. These are some questions to consider. Is the software potentially older or used by a third-party developer? Will the software be capable of handling large data recording at high speeds? Will the software be compatible with any hardware changes? Does the software display and act in accordance with the functionality of the test system, or is it limited? Are you able to configure the screen to see what is important to your testing? As an example, we have encountered a customer who was a battery manufacturer using an integrator to develop test software. Whenever they needed a change to the software, they had to fly in a consultant at a significant cost and delay. With the increase in power comes higher cost in energy consumption. As battery power increases, it becomes less and less economical not to use a regenerative battery test system. An electronic load is an instrument that sinks voltage, current, and power. It uses transistors and resistors to simulate ohmic resistance, which converts energy into waste heat. A lot of facilities still use electronic loads to sink power during battery testing. Bidirectional power supplies can both source and sink power, including a regeneration capability that returns most of the energy to the local grid. There are many companies who must dissipate any excess energy into heat, which can become a big problem with more power being used. Not only can this increase cost, but this can also cause temperature control issues if the facility is not properly ventilated. This is why using a regenerative load, such as a bidirectional power supply or regenerative electronic load, helps control that higher power. The regenerative aspect enables the system to send energy back into the local facility, saving cost of energy consumption and reducing heat emissions. At EA, the regenerative devices, such as the Electronic Load Regenerative, or ELR, have up to 96.5% efficiency to send back into the local facility. The silicon carbon MOSFETs play a factor in our device as a massive advantage. In this slide, I'll be explaining through two different stories. Story number one. A battery manufacturer in the Midwest had a test system made of programmable DC power supplies and electronic loads. Not only did the company have high electric utility bills because of the energy consumed, it also had to run air conditioning to keep the reasonable temperature on the production floor. The test system company's senior applications engineer explains that the company could save nearly $20,000 a month in energy usage if they switched to a regenerative system that returns up to 96.5% of the energy back to the local grid. Before the engineer got home, the battery maker had ordered several systems. Story number two. A charging station manufacturer in the South was using banks of resistors to sink power during a burn-in test. Large blowers carried away the heat and ducted it outside of the building. The noise was so loud you couldn't even hear yourself think. After speaking with the senior applications engineer, they realized they were wasting 100 kilowatts per hour. Managers switched to a battery test system that used regenerative power supplies. The production floor is much quieter, and they were able to recover that energy and monetary value. Resistive loads work with a higher current output and faster response time than a bidirectional power supply. This makes slew rates faster, but with the cost of lost energy and a company not being green. A regenerative bidirectional supply reacts about a millisecond slower, but saves energy cost and helps with the green initiative. Sometimes people add capacitors to the systems to speed up reaction time, but for testing EV batteries, extra speed isn't necessarily needed. The most important part about growing in a high power industry is safety. As of right now, the safety features involve the use of DC contactors. They are triggered if a battery or power supply exceeds the max voltage rating, which may cause fires and irreversible damage on both devices. As the power levels go up, safety becomes even more crucial. Some manufacturers have built battery bunker rooms for their battery testing. Throughout industry, the test system is connected to a battery. If the battery has more voltage than the power supply, the energy will flow into the power supply and it could damage the power supply or cause a fire. If the power supply has significantly more power than the battery could explode. The potential scenario would be a technician manually measures the voltage of the battery with a multimeter before closing the contactors. That technician could have read the value incorrectly or keyed it into the system backwards. It is unwise for safety to rely on human perfection. A better approach for the battery test system is to monitor the battery voltage and wait until the voltage of the power supply and the battery are matched before closing the contactors. Expanding further on safety would be the ability to recognize reverse polarity. There are many batteries in production that are not labeled well on which side is positive and which side is negative. If the battery is square, it could be turned 180 degrees and the technician wouldn't even know it. If they connect the terminals in reverse, the battery is likely to be directly shorted. With this in mind, it is important to know the polarity of the battery and which terminal to connect to. That's why turnkey battery systems include safety features. Before closing the contactors, the system checks for reverse polarity and waits for the voltage to match. In contrast, some test systems have power supplies that are backplaned together, but not all of the power supplies have safety features, which traditionally should be at the system level. Before the start of battery testing on a new system, training is key to keeping you and others safe as well as the equipment. The testing should follow OSHA and NFPA standards, stating that 60 volts or larger requires the use of personal protection equipment or PPE. Manufacturers want to avoid the need for PPE. They want battery test systems that are as foolproof as possible for entry-level workers. The systems should be easy to use to avoid mistakes and to reduce the training required for the entry-level positions that see a lot of turnover. Training should not be overly complicated and skilled. Trained technicians should be the operator of these devices. This training is designed to utilize all the battery test system features safely and should be conveyed in a simple and easy way so that there is little confusion while operating the device. There can be various types of test systems from small to large. It is important to go over the test specifications to ensure the right equipment is used. This is what you will need to do this yourself. In this diagram, we see a cycler cabinet connected to the device under test inside of an environmental test chamber, a PC with testing software, a multimeter for voltage sensing. We have connections from the data acquisition box with leads for voltage and temperature monitoring. Additionally, we have insulated test wires and CAN box communications for control and logging of the device and safety of the test and system. Such features to keep in mind would be temperature, power, and rate of charge and discharge. Such downsides include finding the right software, safety contactors, engineering voltage match, as well as finding space for such a high power system. We have found that our customers have a harder time creating the right battery test system for their application due to the demand of these parts. The contactors must be the best for longevity and safety, which can take time and resources to find. When properly selecting the right test system for your battery, it is important to ask yourself about the responsibility of the system before, during, and after the test. Who will oversee any maintenance needed on the system? Who will oversee software updates and monitoring? And most importantly, who will be responsible for safety? There are many issues with a do-it-yourself approach, which typically requires an outside integrator. Who will maintain the software? Have all the safety features been incorporated? Is the wiring robust? Who will fix it when it breaks? As the industry matures, We're seeing a movement toward turnkey battery test systems. They are pricey but usually cost less than an integrator. Not every company needs a big test system, but if you need a lot of power and channels, they can save you a lot of aggravation. Some battery test systems are designed to test small battery cell. It is possible to connect multiple channels together to increase the amperage, but that consumes most of the system's channels. In contrast, a power supply designed for testing high power batteries offers more power in a compact instrument. The EV battery world is expanding, and it's important to know what the future holds for batteries and their testing technology. Such themes include how the test will be conducted by choosing the right type of test system. How will maintenance and safety be regulated, both software and hardware? How will the production floor change for space and heat dissipation? Here at EA, we have solutions for these growing concerns in the industry. This is an example of what a turnkey solution is for battery testing, the EA BTS 10300. Here at EA, our devices are equipped with a true auto range feature. This allows the user to test at various voltage and current parameters to reach max power. On the left side, this is a diagram of the EA power curve, where there is a clear slope of 5 kilowatts of max power that can be met at either 500 volts and 10 amps or 166.6 volts at 30 amps. On the right side is a diagram of the traditional power curve, only capable of obtaining 10 kilowatts at 500 volts and 20 amps. The traditional power supply is limited to one voltage and one current for max power, while EA power supplies can operate at high voltage, low current, or high current, low voltage, with a full power down to around 33% of max voltage. This can be useful in the battery industry depending on the test that you would need to run. It is important to note that a battery has a charge in it. This charge needs to be voltage matched to any device it is linked up to, or it will cause a spark. If the potential difference in voltage is greater than the supply, it can cause irrepressible damage to both the battery and the device. To ensure a safe way to measure the voltage on the battery, we use a remote voltage sense line. These wires can detect the voltage on the load's terminals. If the power supply is not outputting enough power to the load due to a loss through wires, the remote voltage sense will make up for the lost power by pushing out more power from the device. On this diagram, we have the remote voltage sense lines connected to the load, with a resistor on the hot wire. The source is driving 48 volts to the load, but due to the resistance on the wire, the terminals are only seeing 47.252 volts. The remote voltage sense detects this loss of power to then make up the 0.324 volt loss. Our EA BTS test equipment is an all-in-one turnkey solution for battery applications. We offer a 42U rack that can house up to 300 kilowatts, or a 24U rack that can house up to 120 kilowatts of power in only 6.5 square feet of floor space. Depending on what units are installed in the BTS, a single system can carry a max of 2,400 amps. We also have the availability to customize a system with a PCMC, which can parallel multiple power racks with up to 3.84 megawatts of power to a single BTS channel. The BTS comes with built-in safety features, such as DC contactors, pre-charge voltage matching, as well as the remote voltage sense leads. In response to this demand in the battery industry, EA offers a turnkey solution for a full battery test system. As an example for features to look for, the EA battery test system, or BTS for short, is silicon carbide based for faster switching. It can return up to 96.5% of unused power back into the local facility instead of dissipating it as heat. When I say local facility, I mean it will consume what it can in the building, and excess power may go back onto the local power grid. You do not have to buy a silicon carbide-based solution, but it is the most efficient with a quicker switching rate. Capable of running charge, discharge, and drive tests on your battery. The enclosure offers a throughput design for wires, where you can hook your battery leads outside the cabinet into a testing space. This also includes an emergency stop, which shuts off the power to the cabinet in the event of emergency. This feature is continued through the rear cabinet door, where upon opening the system, will engage the emergency stop feature. What makes the BTS a turnkey solution is the software and the PCMM. This device incorporates its own DC contactors, PC, measurement devices, and internal I/O system. Certain additional external I/O expansion is available. Some additional features include reverse polarity protection and voltage matching, which offers no risk of damaging device under test or equipment from unbalanced voltage matching or improper hookup. Following that is a safe shutdown without opening contactors under load, which increases the life of contactors and the ability to shut down a test due to temperature readings from the DUT or the external thermocouples. These protections offer easy hookup with very little risk in configuring your test incorrectly. The software features the ability to monitor inside the BTS, specifically the temperature to ensure no overheating is occurring, as well as overvoltage and overcurrent. With the use of CAN bus interfacing, the BTS can communicate and adjust current to and from the device under test. Lastly, the software includes easy-to-use features for beginner users. On display is EA's custom PCMM software for the battery test system. It features built-in widgets that allow for multiple displays on a single screen for easy access. This screen is configurable for what is most important for the operator to see and has 10 screens that can be set up. Additionally, it offers a sequence logger, allowing for custom tests to be scripted easily and ran by the click of a button. It also comes with a touchscreen, user-friendly interface, and colored outline for warning and alarm indication. This concludes our webinar. In the next session, I will be taking questions for the Q&A section. Thank you.
Thank you for the presentation. Now we will begin the Q&A session. So if you have any questions, go ahead and click the Q&A button on your screen to submit them. I see that we have a few that have come in. If you could begin by reading the question aloud, that would be great.
Hello, thank everyone for joining. Let's start out with question is, are EA systems available for sale only to OEMs and battery manufacturers, or are they available for sale to independent test labs? All of our equipment is for sale to individual test labs, individuals themselves, OEMs, battery manufacturers. Pretty much you can purchase them in several different ways depending on the size. If you're looking for something smaller, like maybe 2 kilowatt or less, we do work with distribution partners, so you'd be able to find those online. And then the larger systems, of course, you can go to our webpage, which I believe is listed somewhere in the slides. It is www.eapowered.com. I'll also put that link up. And let's see here. The next one would be, how quickly will the battery testing available now become obsolete? Well, if you think about this, right, we've had batteries around for a long time. These testers can be used on lead acid. Obviously they've been around since somewhere in 1920 or 30. I can't remember how far back they go, but quite a ways longer than I am. So I don't see them being obsolete at any point in time, anytime soon. Probably not in my lifetime, maybe not in my kid's lifetime. Although the different types of materials used to create the batteries are changing, we still use, AA batteries for our everyday lives. So, keep that in mind. The next question is, what are the potential risks associated with inadequate battery testing in EVs? That's a pretty large question. So some of the risks obviously are, as we spoke about in one of the stories, your EV catching fire on the side of the road. Um, and you have other items as in, if you have someone that is not trained to work on the systems, they can shock themselves all the way up to death. Um, some other things are, obviously thermal runaway at a smaller level. Instead of consuming your whole car, it may just consume part of the battery, which is the best case, to be honest with you. If the population of the battery pack itself is managed properly, that is what the safety testing is for. It goes in and kind of looks at the separation between the cells inside of the battery pack itself or inside the module, and mitigates the availability for that heat transfer from one cell to another to cause a chain reaction in the cells. How does battery testing impact the performance and safety of EVs? It's a little close to it, but okay. Um, the battery testing itself, you do several different types of battery testing. So obviously there's safety testing where I was talking about the chain reaction for the thermals. There's thermal testing to make sure that the battery is kept at an adequate temperature level in order to get the best efficiency out of it. We also do vibration and shock testing. So if you're driving down the road and you hit those little things on the side of you're going out of your lane a little bit, you hit those little vibrating things, you get vibrations that go out, throughout your car. You hit a huge pothole like we have here in Michigan, half your car falls in. That's more of a shock type situation where you have a large, maybe 10 or 15 G force placed on the mounting parts of what the battery is, parts of the car, which then transfers inside to the cells and all the bus bars and E-plates and however the battery manufactures it inside. So there's a lot of testing done on shocks in that type of way and vibrations in that type of way. But you also have to think of transportation, right? So, maybe you didn't get an air ride truck to take your batteries across the country, and you're going to have a lot of different vibrations and frequencies that they're going to go through. The same thing as if you're driving your car. Some of the other items we do is we test for handling drops. So if you have a module or maybe a smaller battery, a handling drop is pretty much like a 1 meter drop, as if your technician drops it off a table or if it falls off the rollers. That is a handling type drop. There's shipping drops, which are usually, I believe they're 12 to 18 inches, where they drop the whole entire shipping container with the batteries internally in it. So there's those types of tests. There's tests where this is an interesting one. So I had one of my clients a while back take and they basically put a battery pack in the back of a pickup truck, started driving down a test lane in a test facility, and at 70 miles an hour, they just basically pushed it off the back of the truck. So it rolled continuously until it came to a stop. So there's a lot of really cool things about testing that normal everyday things you don't think about. Well, in that particular case, that would be similar to a rollover accident. So there are a lot of tests for that. We have other tests where you do chemical testing. So anything that may be an electric vehicle, even though they don't necessarily have oil for the car spraying or transmission fluids, they have some other items in there. You have your lubes on all your bearings and things like that. So you have to kind of smear that on the batteries themselves to see how the outer case is going to react, and also the connectors. Dust testing, humidity testing, items like that. There's just lots and lots and lots of testing. I've even had somebody drop a pack from 16 feet up. They basically lifted it on a crane, dropped the pack. Luckily, with the rollover test and that pack test, there was minimal damage to them. They had no thermal events. So that manufacturer, or those two manufacturers, did a really good job of making sure that their equipment was in good standing. For an end-of-line test cell, any experience in exchanging energy between packs being discharged, decharged to packs being charged, keeping energy within the test cell and not returning anything to the grid. So we do have a lot of customers, and they do it not only at the cell level, they do it at pack level. For instance, here in Troy, Michigan, at our technology center, we currently only have 60 amps coming into the building, and 60 amp circuit going into my test lab. So there are many times where I need to run a few pieces of equipment that may be above and beyond what we're available to do. So at that point, what I do is I have some more systems that I turn on, and I put those onto another battery. So basically, I've done this before where I've taken and done a discharge on one battery, and I've pushed it into charging another one, so that therefore we have minimal loss, maybe only 4 to 5% going back onto the grid, or loss between the two systems. So if you time your automated system, or if you even start a test at the same time and you have them opposite, where you're charging for 5 hours, discharging for 5 hours, it really never leaves the building. The only time you're going to see anything leave the building is, let's say, it's a hot summer day, a winter day. You don't have your heat running, so the temperature in the building's already set. So you have no HVAC going. You maybe have some lights on, maybe a few people in there with the computers on, and you're doing a high discharge test on a battery. When you get to that point, you will be pushing energy back onto the grid, because obviously you're not using it. So at that point, this is where I suggest, if you have two channels, to just go ahead and, while you're discharging, go ahead and charge another pack at the same rate, because sometimes even the utility grid doesn't really want you to push stuff back on. But so that's just a way to mitigate that also. Okay, let's go with this one. Are you using the BT 20,000 in the BTS system? So currently, we are not utilizing that system at this point in time, especially the triples. There is availability coming for that. It is on the roadmap to get done. I can't really give you a timeline. I'm hoping to get started on it by the end of the year, and maybe have something Q1 next year. But we kind of have to see how things are going along. But there is a roadmap to get to that point. You can use the single channels and just parallel them and use them as a regular PSB in that case. There's no real communication differences as far as the BTS communicating with them. It's just an extra little item that we have to do. So at this point, I would say no. If it's single channel, you're just using them for power, we're going towards that route first, and then we'll get into the multi-channel, where hopefully you'll be able to do up to 24 channels in a single device. So you'll have, that 42 rack should have 24 channels, all controlled by the BTS software itself. This one, is there a better description of your software capabilities? For example, what lab management capabilities do you have? Data, lake, cloud, data analytics. So currently we're still in kind of an evolving phase with this. We wanted to do what I would call like the 80-20. So we're trying to get 80% of what we want to do into the first systems, go through, make sure everything is working properly, making sure our customers don't have any issues. And then we're going to start working on that 20% afterwards. So there is a way to, within the software, upload it to a network drive. So as the test is going and new files are being created, those can be uploaded on the fly. But it is still, the report section is not quite there yet. But the idea is to be able to get everything into one place. Now, I was talking with a third-party person about adding some data analytics in. So that is also on our future roadmap. We're just not there yet at this point in time. Better description of our software capabilities. That would be, if you imagine the screen being a grid, I believe there's 64 blocks available. It's not a drag and drop type of situation. It's kind of like you put the widget on there and you kind of slide it around where it needs to go, and it'll lock into a location. So you can add several different widgets, colors to them, all kinds of things like that. So it is very configurable. Like I said, you have 10 screens, so you can quickly choose between the 10 screens what you want to see at the time. The idea behind our software being widget based is you can put what you want on the screen. Some of the manufacturers just give you what they want you to see, and maybe you can change the graph a little bit. Ours is completely configurable. So if you only want to see a big, bunch of graphs on the screen, you can just put them on there, choose what's graphed in them and see that. You can see numbered values, digital or analog, meters of different types. So there's quite a few different things you can do with that. All right. Will there be a second life market for aging batteries after testing? So at this point, there is second life market things going on in the industry. I do know of probably 3 to 4 places that I've talked to where they are taking those old packs that maybe they came out of R&D, maybe they're just out of a vehicle that had a single module go bad. They are removing everything that's good out of there. If it's a module level, they'll test the modules and place those into a refurbished or newer pack. Where it's good to use. The second part of that is, you take the cylindrical cell type situation. If they're not damaged during the welding process, the micro welding, or if they're just kind of stuck on there in different ways, where they can still be utilized, there's no problem with being able to use those devices. At a module level, you can take something maybe out of I don't want to say any names, but let's say an OEM pack, and they have a module that's running at 96 volts. You may take that 96 volt module out and be able to utilize that in a golf cart, things like that. So in my past experiences, we were using six modules to run a golf cart, but we also would take one of those six to do the we would also take one of the six to go ahead with the sorry, I had an interruption. We took one of those six modules in. Sorry about that. I interrupted here. We've taken one of those six modules out and ran a small robot with it. So, there's always that option to be able to use them in Second Life. We also did some mixed cell testing to try some different things on there. Okay, are these BTS systems available in the UK or just the USA? That's actually a good question. They are available in the US. Now, as far as the UK goes, I believe you guys are on a different voltage scale. I have to check with some of the R&D team to find out exactly when they will be available in the UK. I would assume it's not too long, depending on demand. But we do want to get, quite a few systems out in the hands of everyone. So currently, I think we have approximately 5 to 20 systems out in different production and R&D situations right now. So they will be available, as from my understanding, in Europe and possibly Asia shortly. If not by the end of the year, I would say Q1 or Q2 next year. Do you have state of health testing systems as well? So we're currently working on there is the availability to add it can do DCR, things like that, standard DCIR is not a problem. We are looking into EIS at this point, and we're also going to be integrating, I believe we have to just choose one. We're going to integrate the high pot testing in the next couple months. So that, as the questions come in, as people are interested in the products, we're kind of going with, at this point, who has the most requests, and then we'll kind of go from there and create a roadmap to completing that. Okay, do you foresee a 1500 volt becoming standard for EV electric mobility, or would 800 be the norm for the foreseeable future? Okay, so in this case, it's kind of hard to tell, right? So cars have already gone from 400 to 800 volts in just a couple of years. The reason for that is obviously weight, charging, speed capability, and some other factors. I would say the 1500 volt at the electric vehicle level is probably at least 5 to 7 years out, maybe more, maybe less if we get there. But more on the side of the mobility section, I can see quickly that we're going to have some airplanes getting into that voltage level. Train systems are another one that can carry that high voltage and need that extra power to kind of get through them. So as they think about their busing, they're going to want to change it up to be at higher voltage. So therefore, less current is taken across those bus bars, and of course you'll lose. We'll have the thermal portion of it will be much better. So the norm, probably not for a while, to be honest, but not on the EVs anyways. Maybe the trains, planes, things, much larger items. Ships is another thing that we are working with some companies that do the cruise ships and stuff like that. Sorry, I'm trying to go through these as quick as possible. Do you expect changes for the testing solid state batteries? No, as I explained in the webinar, it doesn't matter what material the batteries are made out of. It's just going to change the power level, and the voltage and current is going to change. But realistically, it doesn't matter if it's solid state. It can be a super capacitor. We don't care what it is. As you saw on the slide, I was talking about the potato vehicle that they were charging the potatoes and running off a potato, and that was just a fun thing. But yeah, it doesn't really matter if it's solid state or not. So the only changes I would see in the solid state portion may be, the longevity of the distance that you can travel. Okay, do you offer also EIS? So EIS is something we're working towards again. So we do have some capability of doing AC over DC currents, but when you talk about EIS, your frequency range is usually outside of our capability with our current function generator that is on our systems. But again, we're looking into adding that third party item into it. So we've had actually quite a few customers ask about EIS lately, and it is something we are working on. Is OEM input required to support the CAN communication with the battery? Okay, so that's kind of a great question, right? So it's a yes and a no. When you look at a battery pack, you have usually up to 3 CAN lines. You'll have a battery CAN line, which normally communicates pack to pack, at least in my experience. And then you have a diagnostic, so something maybe a dealership or the manufacturer would use, which has every one of the signals. And then you have your CAN communication that your vehicle actually communicates at a lower level. So when you plug into a charger, it tells you how much charge I can get, things like that. So you do have to have a DBC file, and depending on what your role is, whether you're a battery manufacturer or a vehicle manufacturer, you would have a different DBC for each of those type of situations. So as long as you have a DBC file, you literally just load the file in and plug the CAN line in, and you're able to see and interact with all those signals. For instance, you may ask the car in a service type situation, you can tell the contactors to open and close. That is something that you can do with our system also. So you just say, hey, send out to this address on the signal line, close the contactors, change it to 1, it closes the contactors, changes to 0, it opens them back up. So there is some input required, but not necessarily from the OEM. If you're the car manufacturer, you have a DBC that interacts with the battery. So yes and no, it's a little gray there. Okay, can you clarify your previous statement? We have 5 to 20 systems in RNG in production now. Do you mean systems installed in total, or 5 to 20 different laboratories? So currently it's we're installing systems every day, so it's hard to keep track of, but it would be different locations. So 1, 2, 3, 4. I believe we're at 5 different locations right now, maybe 6. Systems, there is maybe 10 systems, 10 to 15 in those. So hopefully that answers your question for that. You're welcome, Tim. Thank you. Okay, lithium sulfur. How about suitability on a commercial aspect versus life cycle benefits? Getting deep on that one. So with the life cycle benefits, obviously, the lithium sulfur has a shorter lifetime period. So depending on what you're using it for, it may be better for your application than the lithium ion or graphene, just for the fact that, maybe you're just doing, I don't know, something that you're only going to warranty for 4 or 5 years, and you don't expect, you want somebody to cut. They do it all the time, right? When you buy stuff that's a little bit cheaper, you may be able to save money on cost of the battery, and not expect it to last so long. Let's put it that way. And that point, or maybe you're the battery manufacturer and you want to sell more batteries. That would be one way to do it. Is to look at it as, for the lithium sulfur, you can get it cheaper, but it doesn't last as long. So I guess it kind of depends on your business aspect for that. I'm going to start clicking done on these when I answer. I'm sorry.
We're just about out of time, so we have time for one more question. If you can find one on there, Russ, that you haven't answered yet.
Did that. Sorry. There's a lot of questions on here. I'm sorry. Okay, let's go with this one. So how do off-road conditions impact EV battery performance? That one's pretty short and sweet answer. So I'm an off-road vehicle person myself. I go off-roading, here in Michigan. I spent 4 years in California off-roading there, Gold Mountain, TDS, which is Terre de Sol. Anybody that does off-roading understands what those are. So you can see some extreme things happen off-roading. I've basically jumped my brand new truck over a hill and ended up about 10 feet in the air and came down and blew the rear shocks out of it. You have a lot of jarring, and that's kind of goes into that vibration and shock testing that we talked about earlier. So yes, off-road conditions have a major impact on EV battery performance. And as you can see with the, I believe Rivian does the best commercial that I've seen so far for the off-roading portion. Yeah, it can beat up on them pretty good, especially with water too. A lot of times you're driving through water and mud. So thank you.
Great. Well, thanks so much. Unfortunately, that's all the time we have. We got so many questions. We'll send over a Q&A report to you, Russ, if you want to follow up with people directly. And also, I'd like to thank everyone for attending, submitting the great questions. As I mentioned earlier, a recording of the webinar will be available to view on demand on the session's registration page. Also on that page, you'll find a link to download the slides. And you can also submit more questions via a form on that page to Russ. And of course, feel free to share the link with any of your colleagues that were not available to attend today. So thanks again, everyone, for taking the time to attend, and I hope you found it valuable.